Okay, let's get started. Good afternoon, everyone. My name is Amit. Can you just confirm if you can see my screen where I'm presenting? Can you see the first slide? Okay, good. So I've also again shared my YouTube channel where I upload the sessions that we conduct every Saturday 3 to 5 p.m. And there are also my personal email address in the next line. You may choose to utilize them. And now, so let's quickly get back to our problem solving session. This is our introduction to semiconductor devices, NOC 23E82, hosted by NPTEL. This is the fourth session that we are conducting on August 19. My name is Amit. I'm a PhD scholar at ISC Bangalore, and I specifically work on a semiconducting material called gallium nitride. This so just to have a quick recap that from in the week one we had talked about material classification, and specifically we had seen that in terms of conductivity. Okay, we classified electrical conductivity, that is, and then we saw some basics of quantum mechanics like de Broglie wavelength and Heisenberg uncertainty principle, followed by the some solving Schrodinger equations, time independent Schrodinger equations for quantum wells. So if you recall, the quantum wells, they look something like this, infinite quantum wells, that is. So on your y-axis is your energy or potential. This is tending to infinity, left and right, and this is your well from length 0 to L. X-axis is your length. We saw symmetric, asymmetric wells. Then we also saw some finite quantum wells, something like this in terms of a potential barrier. So again, your y-axis is your potential V, x-axis is your x, and some, let's say, particle is coming like this. So we know classically this you cannot cross this barrier, but quantum mechanically we saw that there is some probability that this particle may appear here. That happens because we are talking a probabilistic regime, not a deterministic regime in quantum mechanics or quantum physics. Finally, we came back to the semiconductor, and we see that how a band gap originates, that due to different, when two silicon or two atoms, they come close together and they can form, and then huge number like 10 to the power 22, 10 to the power 23 atoms come together. They create, they overlap their electronic energies, and we saw how bands are created. And then we saw that how electrons can be excited across this band gap. So we have been expressing band gap as this: top is EC, which is your conduction band, bottom is your EV, and this is your EG, the forbidden gap. So electron cannot, these are the energy states of electrons. So electrons can reside here, and electrons also can reside below EV, but not between this. That's why it's called forbidden energy gap. Then we saw a very crucial concept called the effective mass, using the dispersion relation, which is your EK. E is your energy, K is your wave vector, and so K is 2 pi by lambda. And we saw that this arises that these bands are actually not flat, they have a curvature to them. We saw them, and the double derivative is related to the effective mass. Effective mass essentially captures that all the quantum mechanical effects. So you can forget about quantum mechanics for which we have forgotten to an extent, and just focus that there's the mass is replaced as m star, and you can proceed with your classical mechanics, F equal to ma and whatnot. Then we see that we can dope a semiconductor by doping, which means deliberately adding impurities. If you add donors, that means they donate electrons, that becomes n-type. If you dope it with holes, which means these are electron deficient, and then they become p-type. Finally, we saw the Fermi level, which is where the Fermi function probability is 0.5, and we saw its position in the band gap, and we also saw what's a non-degenerate semiconductor, that is EC minus EF must be greater than or equal to 3 kT, and also if it's a p-type, that EF minus EV also should be greater than or equal to 3 kT. K is your Boltzmann constant, T is your temperature. We saw some expressions using the Fermi function in quantum mechanics. These are, if you just can go through your lecture notes. And finally, we saw the dependence on temperature, that is when at low temperature no dopant is ionized, and then it ionizes partially, and then it's fully ionized, we enter the extrinsic regime. And finally what we enter is the intrinsic regime, where even the bonds start breaking in the semiconductor. And this is from the last session, where we talked about the drift current, that if you apply in an electric field or in the presence of electric field, how it's moving. So we saw that Vd, drift velocity, equal to mu, the mobility, times the electric field E. And we also saw that how its conductivity is related. So we saw that N is the concentration, E is electronic charge, plus Pe mu P. P is your holes, obviously, and N N is your electron concentration. Then we saw non-uniform doping, that how the valence bands and conduction band need not always be flat, and there's a built-in electric field due to that. This concept will come again today multiple times. Then we saw diffusion current, which arises due to the concentration gradient, that is concentration of electron, let's say high is in one side and low in other, that's called concentration gradient, and how they move from high to low concentration. Then we saw total current semiconductor is diffusion current plus drift current, and we also saw Einstein relation linking mobility and diffusion coefficient. Then we saw that what happens when it's not a thermal equilibrium, that is we deliberately inject some carriers means electrons or holes, and we can also shine light, and they can also recombine, which we saw. And finally, this is an important thing, minority carrier diffusion equation, you can go through the lecture notes. And we saw that if we what's happening in a steady state. So steady state would mean that when anything with respect to time, so let's say dp, concentration of holes, over dt is equal to 0. We solved a few questions related to that, and we saw what is a low level injection, that is the excess carriers that we are injecting are low than the background doping. Okay, just as I told, if you have any doubts related to these concepts, first obvious source is your lecture notes, and also the videos. If you are interested, you can go through the videos where we solve problems and went through this concept in some detail. All right, so now let's begin today's agenda. Today we are going to talk about p-n junction, which was also in your lectures. I hope you would have seen them. And what is a p-n junction? So p-n junction happens when a p-type semiconductor on your left and n-type semiconductor on your right, we physically bring close. Assume that there is some distance between them, they're not talking to each other. Let's bring them close. Now you can see they're touching each other. So what will happen? Remember, p-type mean it has access, so it is doped with an A. Okay, so I'm going to denote it by this, by red color. So there are many such things like this. These are the holes, excess of holes. And on the other hand, on n-type you have electrons, which I am denoting by the blue color, excess of electrons. So when you bring them in close physical proximity, so the concentration of electrons is high here and low on the left. So what will happen when you bring close together? Electrons will go from this side to this side. What will happen is that they will leave, because it has donated an electron, it will become, this donor will become positively charged. Let's call this Nd plus. On the other hand, it's an excess of electrons, holes on the left side. So holes will diffuse from this side to this side, right? And they will leave behind a negative charge and A minus, because hole has gone from here to here. All right, so this process continues, and you can see, since it's negative here and positive here, the electric field will develop, right? So it's a positively charged ion here which cannot move, remember, it's fixed in lattice. So electric field will develop in this direction, right? So electric field will develop in this direction, and this will oppose the movement of carriers, because holes want to go from here to here, diffusion, while drift says it should go from here to here. Eventually what will happen is that an equilibrium will achieve, thermal equilibrium, that is. And so what's going to happen is that here what is left behind are just the Na minus layer, and on this side you have Nd plus. And in this region you see there is no more electrons here, and there are no more holes here. Okay, so what's going to happen is that this is called depletion region. Depletion because it's depleted of mobile carriers, that's what we get. This is the depletion width, often denoted by W, and we assume that nothing is happening here it's still n-type. Okay, the charge, so electrons are also here and ions are also here. Okay, Nd plus. So it's like a typical, this is also known as bulk, by the way, on both sides. So it will still behave like an extrinsic semiconductor. In the middle, however, this is called a junction, metallurgical junction. Metallurgical junction. So on either side of metallurgical junction, we'll see the formation of a depletion layer. Okay, so this is a question. Which of the following type is present in the depletion layer of a p-n junction diode? So we just saw this is a p-n junction diode, And we saw that on the p side in the depletion region we have negative ions, okay, and on the right side we have the positive ions. So we see we get both positive and negative ions. This is on n side, negative ions will get on p side, okay. And you also saw there's an electric field, that is, this is the built-in electric field that we'll see in further details, okay. So this is the junction that we saw. Oh, by the way, this is also known as an abrupt p-n junction. Why abrupt? Because this was p-type, so it had some doping, let's say Na of 10 to the power 16 per centimeter cube. So this was doped uniformly, and let's say on the other side you had 10 to the power 2 into 10 to the power 16 cm minus 3. So you see, the if you are moving in this direction, in the x direction, you'll suddenly see this is x equal to 0, the junction. So you suddenly see that doping changes from 10 to the power 16 of p-type doping to a donor type doping of 2 into 10 to the power 16. It's an abrupt change. Hence these are called abrupt p-n junction. Okay. Second flavor we have is linear p-n junction. This means the doping will change linearly. So if I let's say I plot holes concentration, right, so they'll not drop drastically, they'll gradually change, and at this they will reach Ni. So this is your Ni, and then here naturally it will fall below because it's entering the n type, okay. And reverse is true for the electron concentration. So this is hole concentration, right. Electron concentration will rise, and in the middle again at a metallurgical junction it will naturally be Ni, the intrinsic concentration. The other flavor is pin junction. That is p, I stands for intrinsic and n type. So you see this intrinsically is sandwiched between so there are two junctions here, pi and then in. Finally, we have an extreme case of abrupt p-n junction, that is abrupt p-n plus junction. This means we are doping n region very high. This plus denotes that means doping is very high. So let's say the doping here is 10 to the power 16. Here it's, let's say, 10 to the power 18. So 2 orders of difference. That's very large difference. That's why it's n plus denotes that. Okay, so for the time being, we'll forget these three. We'll focus our discussion only on the abrupt p-n junction. Okay, and so what are the characteristics of this depletion region that we are interested in? So we want to know the electric field. I told you there's some electric field that has developed there. The charge profile, what kind of charges reside in the depletion region, the depletion width, as well as the built-in potential. When the electric field is there must be some potential involved. All right, how do we do that? The physics comes to our rescue, which is the Poisson's equation, which is written on your screen over here, but it's very difficult to solve in this region. If you recall the charge neutrality expression, there is p holes, there is n electrons, plus there are donor charges, acceptor charges, and so on. So this equation becomes very difficult to solve in the depletion region. So we make an approximation to simplify. The approximation is that this depletion region between minus xp to xn, right, it does not have any mobile charge carriers. This means it will still have Na and Nd ions, but no p and n, no electrons and holes in this region, which is false. It doesn't happen, but it's an approximation, and it solves the mathematics to great extent. Also, we see that as I told you, this depletion region, and this is a bulk region, or this is also known as quasi-neutral region. This region, quasi-neutral. This is also quasi-neutral. So again, we see an abrupt change. That's the second assumption in this depletion approximation. Okay, so let's apply depletion approximation to this region. So how will the charge profile look like? Charge profile will look something like this. As I told you, this region, since it has donated the electrons, it will acquire a positive charge, right? And this will happen only till xn. Similarly, since the electrons have gone here, or you can see the holes have been donated, right? So you see that holes go from here to here and they recombine with electrons, or the other way, electron come from here to here and they recombine with the holes. Hence there are no electrons and holes in this depletion region. So on this side, since it has donated these holes, or the holes have diffused away, so you have a negative charge, which makes sense. And its concentration, we are assuming this is uniform doping, it will be minus q and a. Minus because holes have been donated, q is your electron charge 1.6 E19, Na is the background acceptor doping. Here it's q and d. Okay, so then we said, then let's acquire the electric field. So we solve this Poisson's equation, and we know V equal to minus grad E. So you see that again, this is also the second form, another expression for Poisson's equation. So del E is equal to rho by epsilon. This is epsilon, not E. E is this electric field. Okay, so that means, so if we integrate this, right, integrate with respect to x, so rho by E dx should give me the electric field, because it's only one dimensional. Okay, and if you integrate this, integration of a flat line is a sloping line, right? So you get this sloping line on both sides. Again, this is minus xp on your left and xn on the inside. This is, again, I'm just repeating everything what's in your lectures, so just to revise everything, that's it. So now we are equipped with all the information, and let's solve some problems. Okay, the questions ask, consider a p-n junction doped with NA&D on p and n sides, and xp and xn depletion with respectively. So this is the problems that we have been talking about, essentially this, right? It's the same thing as that. Charge stored per unit area. Now remember, charge stored per unit area, not per unit volume. That's concentration we are talking about. Okay, in p side of the depletion region. So this means we need to know what is this, the charge. So what's the unit for this? So the units for this will be charge, which is coulombs. So we can say coulombs per centimeter square per unit area, because, okay, so here it's rho, sorry, so here it will be coulombs per centimeter cube. If you want the charge per unit area, right, so let's say I'll denote it by sigma. Okay, that's nothing but integration of rho dx from, we are interested only in p side, so from minus xp to 0. That's only the p side, this is 0. So let's do that. So what's the value of rho? Rho is a constant, so it will come out minus qna, and then integration of dx from minus xp to 0. You integrate this, integration of dx is x minus xp to 0. This will come out minus qna 0 minus xp. So minus qna xp. This is the charge per unit area. Charge per unit volume multiplied by the length will give charge per unit area. So the units will be coulombs per centimeter square. So minus qna xp, this will be your answer. Okay, so is it clear? If you have any doubts till now, I am just warming up. The problems, the numericals will get into later, but because these concepts I'll just assume that you know this thing. Hence, I'm spending a decent amount of time on the very basics of a p-n junction. We are not into diodes yet, just the p-n junction, how a junction is formed, what is depletion width, what is an abrupt junction, how does a charge profile look like. So all good till now? All right. You can stop me anytime. It's fine. I'll be happy to revisit some of the concepts of this class, or if some previous doubt you have. Okay, it's fine. Okay, so let's move ahead now. Just a second, excuse me. Okay, so we have done this thing. Now this next question asks, again, it talks about an abrupt p-n junction. So we have already seen what do we mean by abrupt. Abrupt means on one its p side uniformly doped, on the other side it's n type uniformly doped, but there's a change in doping suddenly, hence this abrupt name. Is uniformly doped on both p and n sides. So this means on p sides is also uniformly doped, n side also uniformly doped. The width of the depletion region is W, as you can see in this diagram, and the electric field variation is given by this E. So we need to plot the profile of the electric field. Okay, this is the same problem which we have done, which I showed you in the notes. This time you can see the position is flipped. You see on the left is n side, on the right is p side. Okay, so how do we solve this? There's nothing new happening in this. Again, if it's n, if it's p, so either or you can see that the electric field we'll just see the direction. We know the profile how it should look like. It should look like a triangle because this is an uniformly doped. Okay, so there are electrons here, right? So electrons will go to this side. So effectively this side, left side, will acquire a net positive charge. Okay, so what's going to happen is It looks something like this. Depletion region will again form something like this. But we see that on the left side it will acquire a positive charge because it has 2 neutral electrons, and here it will acquire a negative charge. So how will the electric field look like? Built-in electric field will be in this direction because it's always away from the positive direction, right? So this is how the electric field profile should look like in both the regions, both the sides, because again this is you see that otherwise it will not any charge will can travel further. Okay, so that's not going to happen. We know that this is an abrupt end we saw in the depletion approximation. So electric field should be positive, right? And we also saw electric field should be, again, this, since it's uniformly doped, so the charge profile will look something like this. So charge profile will look something like this. This is rho. So this is your ND, and this is your XN. This side will be your XP, and this value will be NA, and NA equal to ND. So this will be very symmetrical. The this height on the y-axis will be exactly the same. Hence, if you integrate them, because remember, E equal to rho dx. We just saw that. Sorry, rho by epsilon into dx. Right? So if you integrate them, the integration of both will naturally come out to be the same, and it will be positive because this is a positive side, right? So we saw that, here we saw that if we integrate them, right, so we'll get a positive sign over here. Again, you will get a positive sign, positive slope, so it will look something like this in the first plot. So this will be your correct answer. Or you can simply see, if you want to just to keep at the back of the mind, if it's a PN junction diode uniformly doped, the electric field will be the inverted triangle. And if it's an NP diode uniformly doped abrupt junction, mind you, there are few assumptions here, it will be a normal triangle, of a pointing up triangle, you can say. Again, we'll see that that is it, since it's the doping is same on both sides, so Xn will be equal to XP, right? Or what is the relation between Xn and XP? We'll just come to it in a minute. But is it clear now? Till this point of time, we have talked about the charge profile, we have talked about the electric field profile, and we have also talked about the charge per unit area stored and the nature of charges. Which side will be P side, which side will be which side will be positive charge, the lattice, that is. So these are just keep in mind, these are not mobile, these are immobile. These are also immobile because this is the dopant ions we are talking about. Okay. And depletion region, as I had again emphasized, that there are no mobile charge carriers in the depletion region. So any doubts, any comments till now? Any concept you want me to repeat, revisit, or explain in a bit more detail? All right, let's go ahead now. Further, let's go, plenty of time. Now this is a concept because, as I told you, since an electric field is associated, right, there will be a potential associate. Since the electric field is involved in a PN junction, it will also entail potential, built-in potential, so to speak, right? And so now we'll see that physics we can still understand, but in order to approach or design some material, design some devices, or just to solve some numerical problems, you need to have some at least basic mathematical expressions. So we are going to arrive at that, the physics as well as the expressions. So on the left you have your p side semiconductor, right? So let's draw its band diagram. So this is our EC, this is our EV, and let's assume both are silicon. So this is p type silicon and this is n type silicon. EC and EV. So this will be EG. What is the EG or band gap of silicon? Anyone? I've been talking.
1.1.
1.1. Okay. For germanium? For germanium?
0.78.
0.7.
0.7.
Yeah. For germanium, it's 0.7. Another material which you may encounter is gallium arsenide. I think it is 1.4.
1.4.
Yeah, 1.4. So it's
1.4 thing.
yeah. So it's good to have just an idea, because sometimes, especially in your exams, competitive exams like GATE or NET, in those sometimes it is asked that they'll give a range in the increasing or decreasing order of their band gaps, or for maybe in your university exams, college exams, that is. Or sometimes they might ask which one of the following materials is good for making an infrared detector. Okay, that depends directly on the band gap, so they'll not give the band gaps. So you can still just to, and even it helps to visualize things. Okay.
So won't it depend on direct and indirect?
Correct. Yes, that is true. So also elemental. No, I should not say elemental. Silicon and germanium here are our indirect band gaps. So indirect band gaps means, in if you draw the EK diagram, that is. So I'm drawing the EK diagram here. This is different. So this is a real space. X-axis is your X position. Y-axis is the electronic energy. Okay. So let's just draw the EK diagram for silicon. So this is energy. On x-axis is your k wave vector. Okay, which is its dimensions is centimeter inverse, because it's 2 pi by lambda. So this is your valence band, let's say, for silicon. Valence band, its conduction band lies somewhere over here. Okay, I should not have drawn that line. Just hold on a second. Yeah, so this is the conduction band, and you can clearly see, okay, and this distance is what is Eg. The bottom of conduction band to top of valence band is Eg of silicon. This is silicon, let's say 1.1, which you told me. So you can see there is a difference in the x dimension. This is the indirect band gap. However, for other semiconductors, which I'll draw in blue, let's say gallium arsenide. So gallium arsenide, let's say it's something like this. Don't just forget about the curvature for a minute. Just look at the positions, and it's 1.4, so it will be higher. So it's 1.4 ev, so it should be even higher if I'm drawing to this scale. So this will be somewhere like this. So this is gallium arsenide, this is 1.4. So you can see the bottom of the conduction band and the top of the valence band lie on the same wave vector. This is direct band gap, and you're correct. For applications, for optical applications, or not even optical, for this applications involving photons, specifically LEDs, for instance. LEDs are made for gallium, out of gallium nitride predominantly, right? And for photo detectors, some other materials are used. Fiber optics, I'm forgetting fiber optics, indium phosphide, gallium arsenide, something like that. I'm forgetting that. Sorry about that. But it is used. So yeah, silicon has its advantages, of course, but silicon is not good for uh, devices, or for devices involving optics, photo detectors, LEDs, and so on, because it's an indirect band gap. So good of you to ask. It was a very good point to be raised. All right. So where were we? Yeah, built-in potential. So this is p-type semiconductor and n-type semiconductor. Okay, and its Fermi level, since it's p-type, it will lie somewhere over here, close to valence band. I am denoting it by EFP. Okay, and there will be another for n-type. This is EC, this is EV, and it's because it's n-type dope. This will be its Fermi level. EF, let's say EFN. Remember, these two are completely independent of each other. They do not know each other. So these two are completely independent entities. Okay, what happens when we bring them close? So when we bring them close, you know the depletion region will form. We have been talking about it. This will be, for instance, becomes negative, positive. These are your lattice ions, the dopant ions. All right, but a band diagram will turn out to be something like this. How this is achieved, I'll request you to go through the lectures, but it's easier to see. Just a visualization. Fermi level has to be flat because what we are talking about is the thermal equilibrium. So in thermal equilibrium, Fermi level has to be flat. So you can see EF, which is for this whole device, the PN device, PN junction, it is flat. This means it's equilibrium. And you know, let's just divide it into three sides, three components, let's say. So you see, this is your P type, P bulk, what I have been calling, quasi-neutral region. Here it should behave like a P-type semiconductor, and you see EF is close to EV, P-type semiconductor. On your extreme right, it will behave like an N-type bulk semiconductor, and EF should be close to EC. This is EC, right? It is behaving like that. In the middle, however, you see this thing, and you'll get this because if you recall, electric field was coming of the form of mx plus c, right? This is electric field, and if you integrate it, you'll get the potential. It should come as quadratic. This is a parabola. This is actually a parabola, right? Under depletion approximation, this comes out to be a parabola. You can go through the expressions. I'll not write these here, but this is a parabola that you see over here, and that's how the band diagram comes to like this. But EF has to merge, EF has to stay flat, hence this bend has to bend like this. So you can just imagine that this will come down, sorry, this will go up. So let me just, you have to visualize it a bit in green color. So this whole structure will have to lift up, this whole structure will have to come a bit down, so that these two fellows, the EFs in the middle, they can meet. Okay, there are different ways of visualizing. This is just one way. If you lift this up, lift this down, in the middle the bands have to bend, because EC minus EV, remember everything, this should be EG 1.1, this is EG everywhere, even on this side, on the bulk side, everywhere this should be EG, which we see is happening. For that to happen, bands have to bend in a certain way. Maybe if the time permits, in some future slides we'll talk about heterojunctions. There we'll see some more funky properties coming. Okay, but let's leave it like that, because EG stays constant, so both electron balancement have to bend. And we also know that when the bands bend, this means there's an electric field that is involved. We saw that in the last session also. Same thing is happening here. So the last session that we learned, or the last week that we had learned, we are bringing it on that understanding, we are developing a bit more on that. All right, and these are the expressions. So as I was telling you that so these are the expressions, these have been derived in the class. This is a charge profile that we have been talking about. This is for an abrupt PN junction. Electric field which we saw, it looks something like this, an inverted triangle. Mind you, this is for a PN abrupt junction diode. Left side is P, it's XP, right? And as I told you, if you integrate this electric field, you will get potential. This is a parabola that you will get, right? And we have assumed this to be the reference. The reference can be anywhere, it doesn't matter. Actually, this is the only thing that matters, and this is called V built in. Built in because it's built, you are not applying anything external. This is in fact the property of a PN junction. It's inherent to it, it's built in, right? Like your genetics is encoded in you. You cannot borrow them. You can buy a phone, you can buy a laptop, juice box, anything, but not your genes on a shelf, something like this. It's inherent to this device, hence called built-in. These are the expressions that we have seen. E0 is the peak electric field, which is here. This is important, we'll see why in maybe next class or next to next class, where we see the functioning of PN junction diodes. Okay, this built-in potential, I'm not going to say how it came through, but we'll see in a problem that how it's utilized. So it depends on NA and ND. That makes sense, because how much EF is close to it. If EF is very close to EV and EC, the bands have to bend a lot more. So built-in potential is directly dependent on the logarithmic of the doping densities, right? And we also saw that if you integrate this you should get a quadratic. It looks something like this. These two are same. So if you put VBI here, you can get XN and XP. What are XN and XP? XN and XP depletion width on X and P side respectively. Total width is W. So W, remember, is XN plus XP. Please always remember that, right? And from charge neutrality, the charge here and here has to be the same, because it's electrically neutral, the PN junction. No charge has been injected. right? So whatever the charge, total charge here, it has to be the same in this. Remember we calculated sigma, the charge density per unit area. Same thing, the total charge on the left side has to be the same on the right side of the metallurgical junction. Remember the node, this is the charge density per centimeter cube. I'm talking about charge per unit area or total charge, because area is the same for both n side as well as p side. It's only the length that is different. Okay, so we'll solve some problems, don't worry. These are some expressions which will keep on repeating. I just wanted to emphasize on this square. Where does a parabola come? It comes from here. Alright, so this ends the theory part. So I don't think I'll be touching upon any more theoretical constructs. Maybe towards the end of today's session, we'll have a brief look into the PIN, that is p-type, intrinsic, n-type junctions, and yeah, and one more specific type. Apart from that, everything now from this point onwards will be numericals. Obviously we'll keep on talking about the theoretical constructs behind them, but I'll pause here for a bit, and if you have any comments on questions, please feel free to ask, because from now onwards we'll be applying the things that we have learned till now. Alright then, let's go ahead. So this question says a gallium arsenide p-n junction at T equal to 300 Kelvin. We saw this temperature is important because if you are at, let's say, 0 Kelvin, your Na and Nd will not be ionized, right? Or if you are at very low temperature, let's say at 50 Kelvin, 70 Kelvin, your dopants are not ionized, whether acceptor or donor. It's not fully ionized, I should say. There will be some ionization, but not fully ionized. Okay, at 300 Kelvin, we'll assume full ionization. Also says zero applied bias. This means, as again from previous session we talked about the semiconductor at equilibrium. At equilibrium, we notice that we should not inject any currents, that is apply any external voltage or electric field. Secondly, we should not shine light. So the zero applied bias means essentially it's a thermal equilibrium. These are some important things. So each of these phrase in this very simple, very trivial looking statement has consequences. Okay, and it has doping concentration. So on P side it's 2 into 10 to the power 17. On N side it's 1 into 10 to the power 16. Right, and this is so. What's the Ni for silicon? Ni is intrinsic concentration, you know that. What is the Ni for silicon? Okay.
1.5 10 raised 10
10
per centimeter cube.
Yeah, even if you don't remember the for instance, you are correct, 1.5 10 to the power. Even if you don't remember the 1.5 thing, just remember the order, because that tells you how much carriers are there. So for instance, for this fellow gallium arsenide, intrinsic is only 10 to the power 6, so it has 4 orders lower amount of intrinsic carriers, mind you, than your silicon. Okay, and when we compare the materials, these things become important. Okay, nevertheless, so we are required to find the built-in potential. Very good. So remember the previous formula in your lecture notes and everything, those are for abrupt or step p-n junction. We have already talked about abrupt because the doping changes all of a sudden from p-type to n-type. It's also known as step p-n junction. All right, so all those, so we see, is it abrupt or step p-n junction? The answer is yes, because you see it's suddenly changing from Na to Nd when you go from P to N side. Okay, this means then we can apply the formula that we have seen in our lectures. All right, so Kt by Q is 26 millivolts, which is given. Okay, this is wrong, this is not electron volts, this is volts. 26 millivolts times ln, natural log, Na is 2 into 10 to the power 17, Nd is 10 to the power 16 over Ni square. Ni square would be 2 into 10 to the power 6 whole squared. So 26 millivolts times ln, this will come out to be 33. Denominator would be 12, so 33 over 12 is 21. 5 into 10 to the power 20. Okay, let me just quickly calculate this. So it's coming out to be 1.24. It's coming out to be 1.24 volts. So 1.24 volts. So this is a correct option. Okay, we found the built-in potential in this PN junction. So please remember, this is P, this is N, and if you see the band diagrams, they look something like this. And this is what is called the V built-in, the extent to which the bands have bent till here. Okay, we'll see how to arrive at this particular figure from different aspects, and in the formulas again you will see that why is this term most important. Okay, so we saw that V built in was 1.23 volts. Fine. Now we are required the approximate width of the depletion region on N side. Okay, if you recall, this is the formula from your lecture notes. There's nothing new here, but this is the total width, mind you. So remember, keep on drawing this again and again. So this is P side, this is N side, and this is your depletion region, W. This is your XP, depletion width on P side, this is your XN. Alright, so let's see, depletion width on N side in micrometers. Fine, we'll bring down the units. But W is split into N and P, and this is the expression. Right, this actually comes from charge neutrality. You can just go through the lectures and you'll easily find this expression. So let's try to find the value of Xn then, or let's first try to find out W. Okay, so W would be, now mind this is epsilon silicon, but in this case we'll use gallium arsenide. So this will be gallium arsenide. This will be 2 times 12.9 over 1.6 10 to the power minus 19, 1 over Na, that is 1 over 2 into 17, plus 1 over Nd, which is 10 to the 16, times Vbi, which is 1.23 volts. Alright, so let me get my calculator now, or rather simplify this first. So this will come out to be, this is around 13 into 2. So the first term will come out to be 2 times 12.9 divided by 1.6. This comes out to be 16.125 into 10 to the power 19. This is again square root times 1.23 times, so this term will turn out to be, this is 10 to the power 16. So well, let's say 2 into 10 to the power 17 we take as the LCM, so that's 20. So it will turn out to be 21 times 2 into 10 to the power 17. Okay, 1.23. I have just taken the LCM there, so nothing fancy is happening, don't worry. Times 21, so this is this number 416. So this is turning out to be 41650. Okay, so this is turning out to be 41650. Let me take the square root of that. This is coming out to be 20.4 something. So the question is, what will be the units here? Okay, so let me just see if I'm missing something. Okay, looks good. Just let me find out the square root. 1 2 3 times 21 by 2 8. So it turns out to be 14.43 into 10. I'm getting a micrometer, but I think there's a mistake. Okay, let me just do this first. So this is Na, this is 2 into 10 to the power 17. over Na plus Nd. Na plus Nd will turn out to be 10 to the power 16 plus 2 into 10 to the power 17 into W, whatever this number W is. So I'll try to first say what the point that I was trying to make. Okay, so and as now you can see, this will turn, the numerator will obviously be 2 into 10 to the power 17, and if you see carefully here, this number is much smaller, right? So in fact I can just approximate it as, or let's write it to be the 2.1 into 10 to the power 17 into W. All right, so this is turning out to be 0.95 times W. So this is the point that I was trying to make. Actually, your depletion width, most of it, 95% of it resides on the, so this is a complete width, 95% of it is on the N side, which obviously makes sense because your Na is so high. This means your number of holes is so high as compared to number of electrons. So large, so even from a very thin part of your p side, huge number of holes will come on right side, and hence this length has to be extended. Remember, charge has to be the same on the both sides. We saw that due to charge neutrality, charge can neither be created nor be destroyed. So charge on the left side has to be equal to the charge on the right side. Because the concentration is so high here, the depletion width has to extend on the N side. Okay, this is actually a problem of more of a P plus N junction. Right, so you can see that 95% of it resides on this side. Okay, why I'm getting a wrong answer? I think okay, the epsilon has to come. So can anyone tell me the value of epsilon naught? Epsilon naught also has to come here. Anyone? Epsilon naught's value? It's been long since I have solving problems, so you have to help.
8.85 10 raised to minus 12 farad per centimeter square.
So that's why I was looking for centimeter square. Please remember this. Everything you have to be sure, because Na and Nd are in Cm minus 3. So anything that you put here, right, has to be in terms of centimeters. Okay, so actually it's epsilon, there's epsilon naught also here in this formula. So you multiplied that, what's 8.85 10 to the power minus, can you repeat? Sorry, 14 or 12?
12 farad per centimeter.
12. Okay, so you multiplied this here, and if you do that, you will see it turns out to be something around let me do this. So this is coming 16.125 times 1.23 times 21 by 2 times 8.85. all right, this number, and then if you take the square root, yeah, so this is turning out to be around 430 nanometers. So this turns out to be 0.43 microns. W, mind you, W. So 0.43 microns is your total W here, and if you put this here, so into 0.95, this is around 40.4. So this entity for Xn, right, Xn is 0.41, which is over here. Right, mathematics you can do, that's not a big problem. How we reach there is the, what is your taking, what do you take away from this? So what do we take away? We identify this is a P plus N junction. Why P plus N? Because doping on the P side is much higher, in fact 20 times higher than N side, hence depletion region has to be predominantly on the N side. Hence we see Xn is 95% of the depletion width, right? So you see around 0.43 microns of total width, of which 0.41 microns is on the N side. So barely 200 nanometers is on the not 200, 20 nanometers is on the your P side. It's negligible, it's nothing actually, right? So this is the thing that I want you to take away from this. All right, so we saw that Xn was 0.41 microns and V built in was 0.23, 1.23 volts. Now we are required to find the maximum electric field, and we know the maximum electric field occurs at the metallurgical junction. This is the expression. So we know Nd, we know Xn. Okay, this is gallium arsenide, so just please change that. And the magnitude, so we just forget about this sign here. Okay, Let's just write the expression. So 1.6 10 to the power minus 19, ND is given 10 to the power 16, Xn we have already obtained 0.41 10 to the power minus 6 divided by 8.85, what was it, 10 to the power minus 12. Okay, then this also has to be in centimeter, so this has to be 10 to the power minus 4 length, that is, okay, times epsilon value is 12.9. solve this. Okay, if you solve this, 1.6 times 0.41 times divide by 8.85 and 12.9. okay, this is coming out to be 5.74 into 10 to the power minus 3. Right, so minus 3, this turns out to be one more minus 3, so minus 7 over minus 12, so minus 10, so this is 574. okay, 574 let me just check the units. So minus 19, Na is 16, right, 0.41 and to 10 to the power minus 4, because this is micrometers, remember, if we have to change it to centimeters. So 0.41 10 to the power minus 6 meters. Okay, but so in centimeters this is 0.10 to the power minus 4 centimeters, two places will be gone. Okay, and 8.85 10 to the power minus 12, so you solve this. Alright, 5 points minus 3 and this again a minus 3, so this turns out to be a minus 6 minus 10 divided by, so 10 to the power 2, yeah, so it's coming out to be 574 volts per centimeter. In kilovolts per centimeter, this will be 0.574 kilovolts per centimeter, this one. All right, yeah, so this is just a simple, you put in the expression, you put in the values and you get the answer. It's not a big deal. All right, okay, so from this problem of gallium arsenide, we learned a few things. That first, you need to ensure that it's a PN junction, abrupt junction, only then this formula are applicable. Second, you can also check whether it's an abrupt junction or not. If it's an abrupt junction, life becomes much more simpler, as we see that in this case it's a P plus N junction. If it's a P plus N junction, then what's going to happen is that all your electric field, all your depletion width is going to be in the low doped region. In this case, in ND, we saw 95% of it was there. And finally, the peak electric field, this is an important parameter, and as I told you, it will come in the maybe in the next session when we talk about the breakdown or the breakdown characteristics, avalanche breakdown and all those things. All right, okay, so I'll pause here. Any comments or questions? I may be bad in some calculations, so just just go with the approach rather than the actual number. So I apologize for that if already I have done something wrong. It's highly probable, it's very high probability of that happening. All right, so any comments or questions? No? Okay, so let's go ahead now to our next problem. One second. Okay, I'm seeing epsilon naught values as 10 to the power minus 12. Someone told me minus farad per meter, that is. So then this, I think the last also should change this also. Okay, just as I told you, just make sure that the values are correct. So this will be into 100 into 100. This will turn out to be 57.4 kilovolts per centimeter. Okay, so just I don't have those values at hand right now. This is this actually. Okay, just remember to put in the actual values. Okay, now Consider step PN junction. So again, step PN junction, it's given in the problem, and also you can see from this profile. I told you this is a parabola. You cannot identify it's a parabola or a cubic, but if it's a step PN junction, it's a parabola. Of silicon under zero bias, again zero bias because we're talking about thermal equilibrium. So no current injection, no light shining, no nothing. 300 Kelvin. This means all the donors acceptors on P side, donors on N side have been ionized, all of them, that is okay. All right, so once that has happened, and the doping is not given in this case, but we are given the distance from the Fermi level, and you see it's in equilibrium because Fermi level is flat. See this blue line, horizontal blue line. EC minus EF is given, EF minus EV is given. Let's divide into three parts first. Okay, bulk region on your left, in the middle is your depletion region, on the right is your again N type bulk region. Okay, Ni is given for silicon, someone told me this is the value. Band gap is given, KT is given. We have to find the doping density on the N side. Now this, in fact, this is not even a problem of PN junctions, right? On the N side, if you are given EF, right, from EC, you can find what's a doping. That's, I think, from in week 2 we did that, or week 3, I forget, right? We have done that. So what's the formula? This is the formula that we use. EF minus EI is equal to KT ln Nd over Ni. EF is a Fermi level, EI is your intrinsic level, right? So so Fermi level has been given 0.25 below EC, okay, and this will be Eg by 2. This is the intrinsic level, so Eg by 2 will be 0.56 EV. Then this, what would this be? This would be simply 0.56 minus 0.25, which is 0.31 EV. Let's put it here, 0.31. EF minus EI, EF minus EI, this thing should be equal to KT. KT is 0.026 ln Nd, that's what we need to find. Ni we know. So let me get my calculator first. So it's 0.31 divided by 0.026 and exponential of that, all right, and multiplied by 1.5 into 10 to the power 10. All right, so this is coming out to be, Nd is coming out to be 0.236 into 10 to the power 16. Units is cm minus 3, because remember Ni was in cm minus 3, right? So we approximate it as 2.4 into 10 to the power 15 cm minus 3, which is there, yeah, this is here. So as I told you, this is, we are doing nothing here, and sample at thermal equilibrium on the N side, in fact throughout. Now on the N side we just put this formula which we have seen in the last class from the Fermi level, or you can just see your Nd, just recall your expressions that N equal to Nc e to the power Ef minus Ec, and all those expressions, it's given in your notes, so there's nothing new happening here, right? So the second part of this problem is that we need to find the built-in potential now. Now if you recall the built-in potential formula that we have discussed, right, there we were talking about that how in terms of Na, Nd and depletion widths and all we can express that, right? It's a very straightforward formula. Remember, Na and Nd information is stored in this difference. Remember, we acquired Nd from this, and we can find out what is Na from this. That's a long process. There's a shortcut to do that. What is that? So just imagine that I want to traverse from here to here, right, and then I'll go horizontally like this, and then again I'll come vertically like this, right, and then vertically like this. 1 2 3 and 4, right, and then I am here now on this line, and then let's come down to this level again. Fine, you have come a full circle, right? Energy wise, you raised, then you did not change energy, then you dropped, you again dropped, and then you dropped again. So we have come a full circle, right? Okay, so now we can say that energy that is gained in one part should be equal to, or E1 plus E2 plus E3 plus E4 plus E5 should be equal to 0. On a round trip, the total energy should be 0, right? So what is the E1? You gained EG energy 1.12. E2, no energy change, horizontal. E3, right? You lost some energy. How much? This is nothing but VBI, hence negative, minus VBI. E4, you dropped some more. How much? Minus 0.25. Everything is in EV, mind you. Again, you travel horizontal. I'm not counting that. Okay. And fifth, you drop vertically again. So vertically again is this. This is nothing but minus 0.19. Should be equal to 0. Again, why 0? Because it's a round trip. From this, you get VBI equal to 1.12 minus 0.25 minus 0.19. Let's do that. 1.12 minus 0.25 minus 0.19. This is 0.68. This value is coming out to be 0.68 EV. 0.68 EV. But remember, this is the energy, right? How do you convert energy to a potential? So if you recall, U, the potential energy, is nothing but charge times the potential V. So this is the energy, 0.68 EV. So you divide it by electronic charge, you get 0.68 volts. This. So that's what's happening. How do you balance it with this expression? VBI equal to KT by Q ln NA ND over NI square. You can relate it. You can see that VBI, forget about this factor KT by Q for now. NA and ND have to come at same, they are the same nature, and NI is of the opposite nature. So you see these two things, these are, you can see, are the counterpart for NA and ND, and this is NI squared. EG, if you remember, NI is EG over 2KT exponential. So just to recall this, those three terms have to come in this expression also, and they are coming. This term represents, so to speak, NI squared. These two terms represent the doping on either side, on N side and P side. So this is a good way to just remember, right? Even if you from mathematically you can do that, but not just that. If you are given a band diagram, you can tell the built-in potential, which to put it very crudely is the amount of bend you see in the band diagram. Remember, this analysis that we did here is true for even for non-abrupt junctions, because I'm doing nothing, I'm just traversing, and energy is a more truer concept than the mathematics that was involved to arrive at this expression. So just please keep that in mind. This approach of a coming in a full circle, right, is a more it can be used for more applications, for more devices. Just keep that in mind. All right. And it was a step PN junction, we saw that, right? Okay, so I'll again take a brief pause. If you have any doubts, comments or questions, you may ask. Okay, so if there are no more comments, let's move ahead to the next set of problems. So says consider step PN junction. So we have been discussing all that throughout. T equal to 300 Kelvin, again because all your donors and acceptors have been ionized. At zero bias, this is important, as I have been telling you, because we are in thermal equilibrium, no injection, no shining of light. Only 20% of the total depletion region is P side. Okay, so it's given that XP is 0.2 times W, 20% of W. All right, the built-in potential is given to us, and we are required to find the donor density. That's a very straightforward problem. We again always ask yourself this question: is it an abrupt or step PN junction? The answer is yes. Why? Because the question says so in this side. Even if it were not, you could deduce it from the, let's say, from the charge profile, from the electrical field profile. Just try to keep those profiles in mind. It helps a lot. Okay, So we need to find the donor density. How do we do that? We know this is the built-in potential expression for a step p-n junction, Na and Nd. So we are required to find Nd, right? Very good. Vbi is known, Kt by q is known. If somehow I could find just the Na, right? And how do I do that? I do that because I know this charge neutrality expression. This is coming when you draw the charge profiles. Okay, so there is nothing new that is happening here. So if I do this, so I write Na times xp is given 0.2 times w. Q and q gets cancelled, by the way, and this is nd times xn. Xn will then be nothing but w minus xp, because remember, I'll draw this again. So this is your xp, this is your xn, this is w. So w has to be xn plus xp, total depletion width. Hence xn is w minus xp. From this I can get Na equal to Nd. W minus xp is 0.8 w. You bring 0.2 w down. So Na is 4 times Nd. Again, see, the doping is high on the p side. Na is p side doping, and hence the depletion region there is very low, only 20%. So again you see this trade-off, right, which makes sense because of this charge neutrality. So always keep this in mind. The higher the doping, the less will be the depletion width in that particular region. Okay, so now let's put this Na over here. So what is Vbi? Vbi is 0.67, Kt by q is 0.026 volts, ln Na is 4 times Nd, Nd is Nd over Ni squared. So from this I get 4 Nd square. So let's first calculate this other term. 0.67 divided by 0.026. This is 25.77 equal to ln. This is, you can see this 2 Nd over Ni whole squared. It's 4 Nd square. So 2 will go out, and then the whole thing will turn out to be 2 Nd over Ni is 3.94 into 10 to the power 5. From this you can get Nd very easily. So this is turning out to be 2.96 into 10 to the power 15 cm minus 3. Cm minus 3 comes again from the Ni thing. Okay, so that's our Nd here, and so 2.96. okay, so one decimal place, this is 3 into 10 to the power 15 cm minus 3. Okay, so 3.1 is the closest. 3.1 into 10 to the power 15. So this will be our answer. So how did we do here? Because we need to find the doping for a given built-in potential. That's we use this formula, but Na was also unknown, but Na was given this relation. Xp is 20% of the depletion width. From the charge neutrality expression, we found out the relation between Na and Nd, and Na we replaced here, and the rest is just algebra. That I trust you will do a better job than me, definitely. So we find out the doping, 3 into 10 to the power 15 on the n side, mind you, and if you're required to find on the p side, then you can simply say it's the 4 times that. So it will be 1.2 into 10 to the power 16. All right, that's not required. So let's go ahead on the on to the next problem related to this. So remember, here we found out Nd was 3.1 into 10 to the power 15 cm minus 3. Right, the next problem in this set asks us to find the depletion region in the p side. Okay, so let's first find the total depletion width, and we know that that xp is 0.2 times w, right? So if we find the w, we just take the 20% of it and we'll be fine, right? So now let's just write all that. So this is 8.85 into 10 to the power minus 14. That's epsilon naught. Epsilon of silicon is given as 11.7 divided by 1.6 into 10 to the power minus 19 times 1 over Na plus 1 over Nd. So remember, Nd we obtained as, Na we obtained as 4 times Nd. Na we had obtained as 4 times Nd. So you place it here, 1 over 4 Nd plus 1 over Nd into 0.67, and then 2.8.85 10 to the power minus 14 into 11.7 over 1.6 10 to the power minus 19. So this will come out to be 5 by 4 Nd, and the value of Nd is given as 3.1 10 to the power 15 into 0.67, right? So again, when we solve this whole thing, so this is coming out to be 2 times 8.85 times 11.7 by 1.6 times 5 by 4 by 3.1 into 0.67, and then so that's minus 14, and then that will turn out to be 10 to the power 10. Okay, so square root of this, so it's coming out to be around 5.9 into 10 to the power minus 5. Mind you, centimeter. So this is turning out to be 0.59 microns. Remember, centimeters. And xp we know is 0.2 times w, so 0.59 microns. So this should be around something 0.12. Yeah, 0.12 microns. This is the answer that we're required to find, which is over this. And just let's find out xn also, which will actually something around 0.47 microns. Again, you see that and this value, let me write it down here. This will be 12.4 into 10 to the power 15. So if Na is 4 times Nd, and you can see xp is 4 times lesser than xn, which again makes sense from the charge neutrality. There are different ways of looking at it. I look at it from the charge neutrality perspective, because that I feel will be true in when you have some more complex structures, more complex junctions. PIN will come, there will be different things which will, couple of which we'll try to touch in today's class. All right, so that's from this problem. Okay, so we'll from PN junctions we are done more or less. Now we'll try to solve a few problems on P plus N, or N or Pn plus. So I'll take a pause here. All right, so if you have any comments or questions, please feel free to ask. All right, let's go ahead then. So this problem says, which one of the following is true for a P plus N diode? Remember, it's not Pn, it's P plus N, where plus denotes that P is highly doped as compared to N. And Xp and Xn are the depletion widths. So we have to find a relation with the depletion widths of Xn and Xp. So this is an abrupt Pn plus junction. Remember, this is the Pn plus, not P plus N. So there's a slight difference. Okay, let me analyze for Pn plus, and then we'll flip the result. Okay, as we saw that if N plus is highly doped, so you see the charge value is very high here, right? This y-axis is very high as compared to the y-axis here. It's not looking, so let me draw it like this. Okay, this charge value is very high, and total charge must be constant. This rectangle area must be equal to this rectangle area. If its height is more, its width should be smaller. So I can say that Xn must be less than Xp. It's coming from this expression, Q NDXP should be equal to Q NAXN, right? This is true for, this is Pn plus. When we are here, let's talk about P plus N now. So the analysis here is P plus N. It's different. Q and Q gets cancelled. Okay, so I get Xp equal to, or I should say Xn equal to Just a second. I think I made a mistake. Excuse me. Yeah, so this is an A, this is ND. So from this I get Xn equal to Na over Nd times Xp, right? For P plus N diode, for P plus N, Na is greater than Nd. That's the definition. So this implies Xn is greater than Xp. So that's on the left side you see is the mathematical analysis, right? On the right side is you do it from the diagram or from your intuition. So Xn must be greater than Xp, this thing. For P plus N, mind you, this is for P plus N and this is for Pn plus, where Xn is much smaller than the Xp. We saw different versions of this. In fact, not in Abrupt, we 2 or 3 problems that we saw today. For gallium arsenide problem, we saw that there's a difference of 20 times between the dopings on both sides. And we also see that the depletion width was 95% in one region. In the last problem, we saw that there was a difference in doping of 4 times, right? And for a difference of doping of 4 times, we saw that again it was 4 times, again the same thing was coming in the depletion widths as the doping. So just keep these things in mind. Okay, that's all. That's the summary. That's the takeaway I want you to have here. Okay. If I had not mentioned it before, but in this course, few problems we take, the TAs of this course, they take from the GATE exams. So just the reason for doing that is just to emphasize that the problems that we are talking about here are asked in competitive exams and obviously in your college exams also. So the approach that you develop, that you must develop your own approach first of all. But here we try to different people try to solve it, and whatever you find best, do that. But please make sure that you develop something so that you can approach the questions of GATE, for instance, which you see on your screen. So whatever we've been talking about till now, so I'll try to approach it from my way, right? And let's see what you have learned till now helps or not. Okay, so consider an abrupt p-n junction at T equal to 300 Kelvin. T equal to 300 Kelvin means full ionization. I keep repeating these things because sometimes the GATE paper will say, okay, it's not fully ionized, they'll change the temperature, 0 Kelvin. So P region is not P region then. Nothing is happening. Even Ni is 0 there. Okay. Depletion region with Xn is 0.2 microns. So Xn has been given as 0.2 microns. Doping is also given, right? At the junction, the approximate value of peak electric field, if you have seen the profiles that we have been drawing of peak electric fields, you will notice that it peaks at the metallurgical junction, right? So we are required to find the same thing over here. Okay, and just you can see that the diagram it's a P plus N junction, P plus N region. So you see the depletion region is very small in P side. Even it's in this itself, the diagram, the question shows that. Okay, and it also says Na greater than Nd. So Nd has been given actually 10 to the power 16. Na is much larger than that. Okay, nevertheless, let's just try to figure out the value of approximate peak electric field. Okay, so peak electric field is given by this expression. It's in your slides, so just you can do that. And let's just drop this sign here. So I'll draw it as Emax. This will be equal to QND, because Nd is known, epsilon naught epsilon silicon times Xn. So 1.6 10 to the power minus 19 times Nd, which is 10 to the power 16, epsilon naught 8.85 10 to the power minus 14, silicon's epsilon is 11.7. Xn is given as 0.2 microns, so that will turn out to be 0.2 into 10 to the power minus 4. I'm converting into centimeters. Please just don't make a mistake like I do. Make sure of that your units are correct, because everything you solve correct and you lose marks just because of silly reason of units. Okay, So where were we? Yeah, so this is coming out to be 3.09.
Sir, why you told that fully ionized?
Why? Okay, so we know that for typical semiconductors, so every okay, so I should yeah, I'll write it here. So let's talk only about the n-type doping here. Okay, this is EC, this is EV. So there is something called the dopant level, which we denote it as ED. So just think, assume it's a silicon semiconductor. So this is your EG of 1.1. Okay, and let's say you are doping it with phosphorus, a lot of phosphorus. So at 0 Kelvin, this is how the picture will look like. This means this just below the conduction band energy, phosphorus has, you remember phosphorus is pentavalent, but in order to fit into the silicon lattice, so silicon lattice is, it's bonded with 4, because silicon has a valency of 4. So if a phosphorus wants to sit here, right, it will form 4 bonds, but an extra electron will be free, can be free rather, right? That extra electron at room temperature requires very small energy. At room temperature, the energy which we have been seeing, kT by q, 26 milli electron volts, is sufficient to excite a lot of these electrons into conduction band. An electron is bound to phosphorus, mind you. It can become free if someone can give it some amount of energy. That energy is provided by the temperature. At room temperature, this phosphorus, the extra electron that phosphorus has, can become free. This means at room temperature, a lot of these electrons can jump here. Now you will say silicon also has atoms, electrons here. Yes, definitely, much more than phosphorus. In fact, this phosphorus doping is 10 to the power 15 or 16. Here you have 10 to the power 22 electrons, but this gap is so large. And remember, the probability drops, if you recall, as E minus EF over KT, right? I'll write it again. Sorry. The probability is E minus EF over KT, exponential of that, right? So if the energy gap is smaller here, right, energy gap is smaller, then a lot of electrons can be excited at room temperature, but some energy has to be there. That's why I see, even at room temperature, we'll assume that all the dopants have been ionized. This means they can contribute to the electrons. So intrinsic, for instance, in silicon, intrinsic is 10 to the power 10 at room temperature. But if you dope it 10 to the power 16 phosphorus, that means in addition to 10 to the power 10 intrinsic electrons in conduction band, you will have 10 to the power 16 electrons which have been donated by phosphorus atom. How? Because the bond between phosphorus and its fifth electron is weak enough that that temperature that the temperature at room, that is 300 Kelvin, is able to break that bond, and that electron is free to move into the conduction band, and thus it can contribute to the current. Does that explain? Does that answer your doubt?
Thank you.
Yeah, okay. Oh, so where were we? Okay, so yeah, I was solving this expression. So it was coming like this, and then it again minus 7, and then maybe minus 14. Okay, so this is, units will be volts per centimeter. Okay, so this will come into 10 to the power 4. So this is turning out 31 kilovolts per centimeter. Just rearrange these values, it should be around 31, so the closest option is 30. Okay, again an abrupt, but this time a p plus n junction. Everything else is the expressions we can borrow from the previous discussion on the p-n junctions, and we just replicate the same thing here, right? And this is the peak electric field. So if you draw the profile, right, let me draw it here. It looks something like this. So x, this is your length and this is your electric field, right? This is your p side, so this will be your minus xp, this is your xn, and the area of this triangle, it doesn't look like a triangle but believe me it's a triangle, right angle triangle. The area of the triangle on the left and the triangle on the right are exactly equal due to the charge neutrality. But you can see that the slope is much more gradual here, right? And it's very steep here. Again, that has to do with the doping. In fact, if you dope it like so this is a very exaggerated picture. Actually the picture, if you, in most of the devices it looks something like this, only the right angle triangle. It's so high dope that xp is even negligible, 1 nanometers, even lesser. So this length we don't even care about. This is a more extreme case. So in a more extreme version it looks something like this. xp is non-existent. This is again electric field versus all the electric field is here. Electric field or electric field is dropping here. And that's just we, in fact, many device engineers and material scientists utilize this property. All right. Okay. So okay, so pn p plus n, this was a problem. I'll again pause if you have any doubts, comments till now in the p-n junction, p plus n junctions, or some even basic things like for instance we had used that we tried to find the built-in potential using that total energy has to be zero. I did that loop thing, right? So just feel free to ask any doubts or comments. I'm more than happy to answer. Okay, if not then let's go ahead. So this question talks about if the depletion region in the PIN junction, let me explain this. This means p type intrinsic, n type is w, so depletion width there is WPIN, and in a normal PN junction is WPN. Which of the following is true? Okay, so we had seen that in one of the earlier slides today, and even in your lectures Professor Naresh talks about 4 different let's say flavors of PN junctions that we normally see. We have talked a length in great detail about this. We also saw a few problems on this, right? We have not seen any problems on this, right? In fact, in you rarely find expressions for this. Maybe a few problems, but it's not even practical. It's in practical we don't even see that, because it's very difficult to linearly grading. Control is very difficult. There's one lecture on fabrication of fabrication of that nano electronics, right? You see that this controlling the doping is a very difficult thing to do. PIN junction saves us in that one. For instance, if we want more width, right, we'll see why we need that, but PIN junction can come handy in that. All right, so the straightforward answer is that WPIN, you can see in the diagram also. Why does it happen? So just see this PI, so PI junction, right? We just saw in the P plus N type, doping of P side is much higher than doping of I side, correct? So how will the EK diagram look like? Let's draw the sorry, just a second. Okay, so this is my x-axis, this is my xp, this is my minus x naught. So this is this region. Focus only on this. This is highly doped, this is very low doped as compared to P. P is very high doped as compared to intrinsic. So what will happen? How will the diagram will look like? There will be virtually no depletion, or if I'm drawing the electric field diagram, right? Let's say this is E. What will happen? So this xp will be virtually non-existent, right? All the depletion width will be in the intrinsic region. So I can write that xp will be much lesser than X intrinsic. Similarly, on the right side, n type is much higher doped than your intrinsic. So again, xn which be much lower than extrinsic. So what is the total depletion width? Total depletion width is xp plus xi plus xn. So I can just drop xp and xn because they're much smaller than xi. So w will be equal to xi, it is the intrinsic length. And since doping, you remember doping here is 10 to the power 16, let's say. Here doping is what? 10 to the power 10. That's the baseline, right? So usually if this is 1 micron, right, this will be 1 meters. It's not realistic. You don't find devices 1 meters long. So even for moderate doping, 10 to the power 15, 10 to the power 16, this means that this whole thing, which is a few centimeters, at the most few centimeters, it's not even a centimeters, maybe a few microns, this whole thing is depleted. Okay, so how will the diagram look like? Diagram looks something like this. So xp is virtually not existent. Okay, so minus xp will look, this will look something like this. Will peak here, peak here. Just a second, let me draw it properly. Right, so it will peak here and then it will remain constant. Why constant? Because electric field will remain constant, because there's no charge here in intrinsic. Remember that. It's not doped, there's no acceptors or donors in the intrinsic, hence the charge will be 0 here. And again when you come on this junction on the other side, it will again rise. So this will be your xn, this is your actually xp. I am exaggerating it a lot, but this is the true picture mathematically. Okay, this is a very high exaggeration of PIN diode. Okay, so hence, because usually we saw that in PN junctions we saw the depletion bits of not even a micron, 0.4 microns, 0.3 microns, 0.1 microns. This intrinsic region itself is a few microns, 2 microns, maybe 10 microns even. So usually what we see is that the WPIN, right, WPIN is of the orders of few microns, right, and WPN, the depletion within PN, is smaller than mu. In fact, it can be much smaller for modern devices. So that's why we conclude that the WPIN is greater than WPN. You can also say that it's insufficient data. For instance, I don't know what are the dopings, what is the length. For a typical doping, that's why I'm saying, for a typical doping, this should be true. An average PIN diode will have a much larger depletion width than an average PN diode. That's the lesson that I want you to take away from this problem. All right. Okay, so we are done with PIN. I'll pause here because it might you might get a bit confused. The electric field is flat, how the charge profile looks like. I'll pause here. If you have any doubts, you can ask me. Okay, fine. If you, and that's why I told you, if you don't feel comfortable talking right now, okay, we do this again. So you are highly encouraged to ask questions on the forum. You must be seeing that people are using that. If not, you can write to me personally. This is my email address in your chat box. I've also given the link of my YouTube channel where I upload these recordings of the sessions that we conduct here. All right. Okay, so let's move ahead now. This is a different kind of problem which we have not seen till now. Earlier we were seeing in doping PN junctions. This is something else. Let's try to solve this problem. It says that consider a uniform p-type bar. So this is some semiconductor bar p-type, both sides throughout it's doped with Na acceptor dopants, within which a thin sheet of positive charge has been embedded. So due to some manufacturing defect or whatever, it has a thin sheet of a charge QP. The charge is fixed in lattice and cannot move. This is important. This is not mobile. This is like your lattice ions, right? They're fixed. This forces the majority carrier holes to rearrange and satisfy the Poisson's equation. Remember, all this analysis was started from the that in order to solve the Poisson's equation, it's difficult to solve that, so we've made a depletion approximation, right? So this problem takes us back to that analysis. So here it's different, it's not a PN, but still, since a positive charge, remember there are holes here throughout, uniformly distributed. So what's going to happen, these holes will feel a repulsion from this positive charge. Positive charge, this has to stay, this cannot go anywhere. So it will have an electric field, right, in this direction, and then in this direction, away from it, right? So holes which encounter this electric field will be pushed away. So the holes will be pushed away in this side. On the right side, holes will be pushed away to further right. On the left, they'll push to further left. Okay, and we are required to find how does the electric field profile look like. Okay, so let me just try to say try to just elaborate on what I was saying earlier. So the electric field must be on the right side. This means a depletion region will form here, something like this. So here you will have your dopant ions. Similarly, same thing will happen here. The holes will be, due to this repulsion from this positive charge, they'll be pushed away, right? That's how the picture something look like. Again, it has to be same on both sides, because Na on this side, Na on this side. Okay, so let's call this x1, let's call this x2. First thing we notice is that x1 has to be equal to x2, right, because the doping is same on the left as well as the right. Second thing what I notice is that the electric field direction will be something like this. In the right half, it will be towards the right, so it has to be positive. And again, if you solve this, since we have now drawn the charge profile, right, so you remember this, the Poisson's equation, if you try to solve it, right, then you mathematically you can also obtain that this has to move towards right and this has to move towards the left. Okay, so and it will also be linear because rho is a constant here, right? So E is linear, electric field must be linear because rho is constant with respect to x. So E must be linear. Okay, so this is the information that we can derive. Now let's find in which of these options is this true. So remember, first thing we solve that x1 equal to x2, symmetric, must be symmetric. And second, E is linear in depletion region. Where is the depletion region? Here is the depletion region. Okay, so you see x1 equal to x2, that looks to be true in all the graphs because this is minus xp, this is xp. Okay, so this is satisfying. E is linear in depletion region, so in this region E has to be linear on this side as well as this side. So this is incorrect, this is also incorrect. E is flat here. Okay, also one more thing we notice is that that E has to be positive here. So E has to be in positive direction. Here E has to be in negative direction. Okay, so this is not correct because here also on the right side E has to be in positive direction. This option cannot be correct, this cannot be correct, this cannot be correct, this is the only correct option. I'll reiterate, x1 equal to x2 because the doping is same on both sides, so hence this has to be symmetric, so all the options satisfy that. Second, E is linear because we saw that the charge distribution here is constant in space and we use a depletion approximation that this boundary is abrupt and so on, correct? So when we saw that that this E has to be linear if you solve the Poisson's equation, so yes, so these two options were eliminated. Then finally we saw that on the right side E has to be positive, so on the right side E has to be positive, this option satisfy, but on the left side E also has to be negative. Okay, and this option satisfy that, only this option satisfies that. All right, So that's how this was a, I mean, different flavor of a problem, because PN junctions we have been seeing throughout. But here what happens when we add some non-idealities, because actually in manufacturing or due to some other reason this can happen. This is not something that's only restricted to your numerical problems. This happens. All right. Okay, so that is that. And you also notice one more thing which should be fairly clear. The E peak here has to be the same, right? So it's E peak, the magnitude. Here also it's E peak. They are both the same. The direction is just the sign is inverted because the direction is inverse. We saw the analysis here. The right side it has to be positive and left side has to be negative. Okay, so that's the first part of this problem. The second part says the built-in potential across the junction is. Okay, now that's an interesting problem. We again, you see, it's the abrupt junction formula that we have. These are not applicable here. That's true for a PN junction. There was no charge embedded like this. Okay, so how do we approach this? So we approach this because we have solved the electric field problem. This is the electric field. This is X, and you know that E equal to minus grad V. So V I can obtain it as integration of E del X. This means you integrate this plot and you can get the voltage. Now if you integrate this area, which I'll highlight in, so let's break this integration first. I'll write it as E negative from minus xp to 0. This is minus xp, this is xp, and here is your depletion region, minus xp to xp dx, and there is a minus sign here, so that stays there. And then let's drop from 0 to xp. I call it as E positive dx. So here in this region, whatever the electric field is, I'm calling it as E positive. Here I'm calling it as E negative. Okay, now integration is nothing but area under the curve. Okay, so the area under the curve, this is the green term here. Okay, similarly this is the blue term here. The magnitude will be exactly the same. How do I know that? Because I told you this peak is the same, right? So their area, to calculate the area, right? Area green, right? This will be half xp E peak, which will also be equal to area of blue, same, but in opposite sign, because here E is negative, here E is positive. X is progressing from this direction to this direction, hence these two terms will cancel out. So V you will get equal to 0. Why I'm getting V? Okay, fine, I got this V built in. This is a mathematical definition. It's nothing but integration of electric field, built-in electric field, that is built-in. This is the thing that I want you to remember, and just ask yourself that is it true or not. I told you in the, I don't know, in the earlier parts of today's session, that every electric field that we encounter, it has associated to it a potential, electric potential. And this is a very good example. We have been just, I told you when the, for instance, for abrupt PN junctions that we were talking about, we saw that electric field was coming out to be a triangular, triangle, but it was a straight line, right? We integrate that, you get x squared. We also saw a mathematical expression for that in your lecture slides, if you recall. And then I saw when I draw the ECEV, I told you that okay, you see this bend as I told you that I just told you that it's a parabola. Fine. Again, that built-in potential that was arising due to an electric field, right? If you integrate that, you get the built-in potential. Same principle, that's a principle of physics. The device may change, you can incorporate this charge here, positive charge, negative, you can incorporate any number of charges. The problem of physics, the Poisson's equation, will still stand. It has to stand. Okay. And here again we started with the Poisson's equation, then we figured out, then we applied the depletion approximation. You see here we applied the depletion approximation in minus xp to xp, right? And then we obtained that electric field has to be linear. We also saw electric field, the magnitude has to be the same, it has to be symmetric, because this was a uniform p-type semiconductor in which a charge was embedded. And then if we integrate it to calculate from the built-in electric field, you can calculate the built-in potential, electric potential, just integrating that. And we see that the green region and blue region, they are equal in area, but they have the opposite sign. Okay, hence the built-in potential for this specific semiconductor bar, which was uniform p-type bar with charge embedded, it will be 0. If the charge were negative, again it will be 0, the built-in potential. Okay, so this is a again this so the different types in which this problem is seen. Maybe when the professor touched upon some aspects of manufacturing, which we have seen, I think a lecture has been there on manufacturing in semiconductors, fabrication of devices, right? So this is a very realistic problem that is encountered, but fortunately, right, although there is an electric field associated to that, but the built-in potential is 0, so it's not impacting us potential wise, but electric field is there. So if it encounters any, if we inject some carriers, right, let's say electrons or holes, it will play a role. For studies, for equilibrium, it's not playing a role, it does not seem to be playing a role, but that's how you approach these problems. Okay, so this was the problem. So the very, I mean, this just condensed everything that you have learned. If we solved all the problems which were based on the formula, but then in this problem we went back to where we started. All right, that is solving the Poisson's equation after and applying the depletion approximation. Okay, so any comments, questions you may ask. This is the second last problem. I have one more problem after this. So all right, then let's go ahead with the last problem of the day. So again, this problem asked in GATE 2021. So silicon p-n junction is shown in figure below, is made with densities is given on p side and n side. You can see that p and n are different length, 1.2 micron, 0.2 micron respectively. Built-in potential is given, permittivity is given, right? The magnitude of reverse bias voltage that would completely deplete one of the two regions prior to the other is. So forget about the term reverse bias for now. Let's just see what it's talking about. So when p and n junctions are brought into contact, they'll form a depletion region, and you can see that the doping of n side is higher. Okay, this means the depletion will be more in p side. We have been talking about this. So on n side, let's say this is the depletion region. P side it will be slightly more. Okay, let's call this minus xp, and let's call this xn. Right, this is now at equilibrium. This means there's no external voltage that is being applied. Correct? Right. So, but what happens if we apply a voltage? A reverse voltage, it says. Reverse voltage means on P side, okay, I'll draw it in a different color just to differentiate. Okay, reverse voltage means P side will be connected to the negative terminal of the battery. So this is what we call the reverse bias. Let's say its magnitude is VR. Whatever the voltage that we are applying is VR. Okay, this is the expression, right? So how does this expression change? Its only change is like this. That's it. This is the only small change that it happens, that VBI will become VBI plus BR. That's it. How it comes, we'll see in the next class when we talk about reverse biasing a diode. But this problem can be solved today also. So VBI plus VR. Okay, fine. What will happen is that this region will now, which the region that you see, the red is your thermal equilibrium, and as you apply a bias, it will keep on shifting in this direction. Same goes for this, it will keep on shifting in this direction. Who will deplete it? Who will deplete first? That's the question, right? Okay, so let's just find out at equilibrium what's the situation first. Okay, so actually intuition tells me that this is going to be depleted first. Okay, so let me do that. Let me assume that left side is, the n side is depleted. These are the expressions for that, right? And you can confirm that by n times will be depleted. So you see this term W by Na plus Nd will remain constant. The only thing of difference is xp upon Nd and xn upon Na. Xn can go maximum to 0.2 microns. Then this will complete thing will be, that's what we want, right? And xp can go to 1.2 microns maximum. And Na and Nd have a difference of just a factor of 2, but they have a factor of 6. So this tells me this will be depleted first. If there was a factor of 10, right, then this would have won, because 1.2 by 10 what will be 0.12. This will still be 0.2. This is depleted first because W and this term, the right, W over Na plus Nd is same for both of them. So as you increase VR, this thing, as you increase VR, W will increase. This term will keep on increasing. This will remain constant, the denominator. Numerator is also constant. So what's happening? XV and XN will keep on increasing. I'm denoting here. They'll keep on increasing. Just because that Nd and Na are not too much different, right? But their lengths are different. The physical lengths. This will be depleted first. Okay. So now what do I do? Now I know this will be depleting first. So I write Xn as 0.2. I assume that N side is depleting first. So N side is depleting first. So I'll write it as, I'll take this. I'll take 0.2 microns equal to Na over Na plus Nd. So this is 5 into 10 to the power 16. Remember the formula is something like this. And this is 5 into 10 to the power 16 plus 10 to the power 17 times W. From this I can get that W equal to, so this is 5 divided by, it will turn out to 15, 1 by 3. So this will turn out to be 0.6 micrometers. It's very simple calculation. This is 2 into 10, 10 into 10 to the power 16. Yeah. So W is coming out to be 0.6 microns. In that case, this will be depleted completely. This will turn out to be Xn here, and this will be gone something like this. 0.6. Mind you, this is when I am applying a reverse bias. Please note that I am applying this reverse bias VR. W's value is this now. So let's put the value of W here in this expression. Turn out to be 0.6 microns equal to square root of, square root of 2 times epsilon naught. Epsilon SI is given 12. You put the electronic charge Q. You put the value of Na and Nd, which is given. VBI is also given, which is 0.8 plus VR. Put this plus VR, and from this everything is known. So from this you can get VR. You can get VR. So let's try to do that. Let's try to find out the value of this VR. Okay. So it will be, we must calculate what's under this thing, the square root. Okay, so that 8.85 into 10 to the minus 14 into 12 divided by Q is 1.6, right? and then we do 1 by NA plus 1 by ND. So that will turn out to be that's 1 by 5 into 10 to the power 16, and that's 10 to the power 17. So that's 0.5 into 10 to the power 16, 0.5 10 to the power 17. So that will not be 1.5 into 10 to the power 17. Okay, so let's do that. 1.5 times that term will remain the same, and then it will be 0.6 squared. Then we take it to the other side, so VR plus 0.8 is coming out to be this squared 10 to the power minus 8 plus this is turning out to be around 9 volts. Okay, from this, if VR plus 0.8 is 9 volts, I put this here, so this gives me VR equal to 8.2 volts. The value of VR is coming out to be 8.2 volts. Okay, just don't worry a bit too much about this problem, because when we talk about reverse biasing a PN diode, this concept will again come into the picture. Why I wanted to bring it up here now is just so that you can visualize this, that as we increase the VBI not as we increase the bias by some reason, W will increase, and W will increase on both sides. So negative side, so Xn will keep on extending towards right, XP will keep on extending towards the left, because W is increasing. All these terms are constant, but since ND and NA are not much different, only a factor of 2, right, what will happen is that Xn upon NA, right, this factor, because W over NA plus ND is constant, Xn will reach 0.2 first. When Xn was 0.2, XP was 0.6, right? So this means N region, as you keep on increasing the bias, N region will deplete first. What actually is happening is that although this region is neutral, this is applied to a positive bias. So what will happen? The holes will keep on coming from this side, and they'll keep on recombining with the electrons, and thus there'll be no mobile carriers left on the N side. Same goes here. When you apply a negative bias, means electrons are coming, and this is a hole rich area, so electrons are coming, they'll recombine with holes, and thus there'll be no mobile charge carriers left on the P side also, right? But we saw that as soon as you deplete the 0.2 microns on N side, the P region is not completely depleted. We saw at 0.6 microns is still left, so N side is completely depleted first, and thus we use the N side formula, right? You can also use P side, but then you have to put 0.6 here. So Xn you put 0.2, which we did here. You see here, W we obtained as 0.6. Sorry, if we obtained W as 0.6, I made a mistake. This will be 0.4, because this is 0.2. So 0.2 plus 0.4 is 0.6, and then you can clearly see, you just put all the values that you are here. You obtain V 0.8 plus VR as around 9. VR you get as 8.2 volts. All right. So that is how we solve these kinds of problems. This again will come in the next class, hopefully. So yeah, that's it from me for today's session. If you have any doubts, any questions, conceptual, numerical, from this class, previous class, any assignments which have not been due for submission, for which the due date has passed, just I'll stay back for a few more minutes. You can ask me. All right. Okay.
Not yet, sir. Thank you.
Okay, thank you. Thank you. Then if there are no comments, I'll be closing this session. Thank you for joining. Hope to see you next week.